everyone. Today we are beginning Unit 9, which is about trigonometry. To begin, we're going to start with Section 1 that covers special right triangles and trigonometric ratios. So first we have draw a triangle in the space below with an angle measure of 45, 45, and 90 degrees. Label the legs of the triangle x, and then use the Pythagorean Theorem to find the hypotenuse. So I already drew this triangle here, and you'll need to take a second and sketch this out. And this is a 45, 45, 90 triangle. So I'm going to label my angle measures here. So I have 45 degrees and 45 degrees. One thing that I know about a 45, 45, 90 triangle is that it has to be an isosceles triangle because these legs are congruent. So this leg is congruent to this leg, and it tells us to label them both as x. All right. So this is going to act as a formula. Anytime I have a 45, 45, 90 triangle, this leg, whatever it will be congruent to this leg, and the value of that length we're representing with x for right now. To find the formula for the length of the hypotenuse, we're going to use the Pythagorean Theorem and these variables to solve for our missing side. So I have a squared plus b squared is equal to c squared. That's the Pythagorean Theorem, and now I'm going to plug that in with my leg names. So I have x squared plus x squared is equal to c squared. X squared plus x squared is the same as 2x squared, and that is still equal to c squared. Now the thing is, we want c to be by itself. So to get c by itself, I need to take the square root of both sides of this equation. In doing so, that gives me that c is equal to the square root of 2x squared. Now, if you remember, when we are using a radical, we can split our multiplication up into two separate radicals. So instead of c is equal to the square root of 2x squared, this is equal to the square root of 2 times the square root of x squared. Now that I have this here, I can cancel out the square root and the square to leave me with just x. And I'm going to rearrange this all in one step. So I have c is equal to x square roots of 2. So that's telling me that the hypotenuse of my triangle is equal to x square roots of 2. Now you're never going to have to solve this piece on your own in this class, but you do need to know the formula for the side lengths of a 45, 45, 90 triangle. And that formula is right here. The legs will be congruent, and the hypotenuse is the length of one side length times the square root of 2. All right, so that's our general formula. And that leads us to this 45, 45, 90 triangle theorem that says that we have a special isosceles right triangle where two legs are congruent and the non-right angles both measure 45 degrees. Let's take a look at a couple examples of how you would solve with this. So we have that our side length here is 8, and this is one of our legs, and the other leg isn't marked, but because it's a 45, 45, 90 triangle, this has to be 8 as well. That leaves us with our hypotenuse. And our hypotenuse from our formula is equal to one leg times the square root of 2. So our unknown piece here, our x, is equal to 8 times the square root of 2. And we're just going to write that right as is, 8 square roots of 2. All right, let's take a look at another example, same type of thing. It's a 45, 45, 90 triangle. We know the legs both have to be 5. So the hypotenuse is equal to 5 times the square root of 2, meaning our missing side is equal to 5 square roots of 2. All right, so that's what happens if you're given a side leg. That's what happens if you're given a leg of our triangle. If you're given a hypotenuse, this changes a little bit. So we're still using our formula. This time we know that our hypotenuse has to be equal to x square roots of 2. That means that this 2 square roots of 7 is equal to x square roots of 2. And by setting it up this way, it is allowing me to solve for my missing side which we're referring to as x in this problem. And that will be the same for both of these. And just to clarify, I know this is a 45, 45, 90 triangle because I have a 90-degree angle here, and these legs are marked as congruent. That means that these angles also have to be congruent, which means they have to be 90 degrees. All right, so back to our problem. So we have x square roots of 2 is equal to 2 square roots of 7. I'm going to divide out the square root of 2 on both sides, and that leaves me with x. And I'm going to divide this out on a calculator, and I'm actually going to pull my calculator up right here. So I have the 2 square roots of 7 on top. And notice I'm going to hit this right arrow key to get out from under the radical sign. Then I'm going to hit divide by the square root of 2. Going to again hit the right arrow key, and then I'm going to hit enter. And this calculates that whole thing for me, which is 3.741. 1 is not high enough to round our number up, so that is approximately 3.74. All right, and I'm going to leave my calculator up for a little bit because we're going to need it on the other side as well. So we have another triangle here. We have x for my leg. We don't know anything about this leg either, but we do know that the hypotenuse is equal to 9. By the formula, 9 is equal to 1 side length, which is written as x, times the square root of 2. That is our formula. So I'm going to again divide out the square root of 2. In doing so, that gives me that x is again going to be a decimal. Let's type this in. So I have the square root, or I have 9 divided by the square root of 2, which is equal to about 6.36. All right, and now let's get rid of this calculator here for a little bit. We'll need it again soon. All right, so that is 45, 45, 90 triangles. We also have another type of special right triangle, and that is the 30, 60, 90 triangle. And this triangle has this theorem that says that the hypotenuse is equal to 2 times the leg of the shortest side, or the shortest leg. So hypotenuse is 2 times the length of the shortest leg. We don't know what that length is, but we can figure out using a variable. So let's say that our shortest leg is x. Then that means that our hypotenuse has to be 2 times that x. So we're going to label that as 2x. All right, before we go any further, I'm going to label my other angles. Because this is my shortest side, then this angle across from it has to be the shortest angle, the smallest angle. So this one is my 30-degree angle. And this angle up here then has to be 60 degrees because 90 is already marked. All right, so now we have x for our shortest leg, 2x for our hypotenuse, but we don't know the length of the third side, the second leg. So we're going to use the Pythagorean Theorem to solve for the formula for this leg. So I have a squared plus b squared is equal to c squared. I'm again going to write that out using the measurements that we already know. So I have x squared plus b squared is equal to 2x squared, and that 2x is all being squared. So it's all in that square. I'm going to start by simplifying this out. When I have 2x squared, that means I'm squaring both pieces because this is multiplication. So I have 2 squared, which is 4. And then x will still be x squared. So I have 4x squared, and that's equal to x squared plus b squared. I want to get b by itself. Before I can do anything here, I need to get everything else off of this side. So I'm going to subtract x squared from both sides. That leaves me with b squared is equal to 3x squared. Like before, I'm going to take the square root to get b by itself, which means that b is equal to the square root of 3 times the square root of x squared. And again, this x squared is under a square root, so that cancels. That leaves me with b is equal to x square roots of 3. Now that I know that my other leg is x square roots of 3, I have a formula for all 3 sides of my triangle. This is again for a 30, 60, 90 special right triangle. All right, let's take a look at some examples. So I have this triangle here, and I have 5 for my shortest leg. That means that to find the second leg, I need to multiply this by the square root of 3. So I have b is equal to 5 square roots of 3. Then I know that if this is 5, then I need to multiply this length by 2 to get the hypotenuse. So I have 5 times 2. So c equals 5 times 2, meaning c is equal to 10. Now I have all 3 side lengths. Let's take a look at another example. So in this example here, they gave us the hypotenuse, but they didn't give us either leg of our triangle. So I can use my formula knowing that my hypotenuse is equal to 2 times the length of the shortest side, which is represented with an x. So in other words, 22 is equal to 2 times x. I'm going to divide out the 2 from both sides. So 22 divided by 2 gives us the length of our shortest side, which is 11. Now that I know my x, my shortest side, I can use that to find my other leg, because I need to multiply this by the square root of 3 to get this leg measurement. So I have 11 times the square root of 3, meaning y is equal to 11 square roots of 3, using the formula. All right, we have another example right here. This one's a little different because it gives us our second leg instead of either the shortest side or the hypotenuse. This leg is the one that is equal to the square root of 3 times our shortest side. So I have 15 is equal to x square roots of 3. I'm going to divide out the square root of 3 from both sides. And that gives me that x is going to be another decimal that we need to use our calculator for. So I'm going to pull my calculator back up. I have 15 divided by the square root of 3, and just typing it all straight in. That gives me x is approximately equal to 8.66. All right, now I don't know how well this is visible to you, but this gives me this really long decimal, 8.6602540378. When I'm using this x for the rest of my problem, I'm not using this whole decimal. I'm going to use the rounded answer that I wrote down. So when I'm solving for y, which is 2 times this length, instead of typing in this whole decimal, I'm going to say y is equal to x times 2, or in other words, 8.66 times 2. So y is going to be approximately equal to, not equal to, but approximately equal to 17.32. Make sure if it is an approximation that you are using this approximately equal to, not the actual equal sign. All right, we're going to slide this over and look at our last example here. So this time we again are given the hypotenuse, but this time we have a radical symbol in our hypotenuse. So I'm going to plug this into my formula. So the hypotenuse is equal to 2x. So 2x is equal to the square root of 6. I'm going to divide 2 out on both sides, and I'm going to need to plug that one in again. So I have the square root of 6, get out of the radical sign, divided by 2 is equal to 1.22. That's my x. Now I could leave this as the square root of 6 over 2 if I wanted an exact answer, and then I would plug this whole thing in for the rest of it, but I'm going to use a decimal for this one. So to find my other leg, I need to take the shortest leg and multiply that by the square root of 3, which means that y has to be equal to 1.22 square roots of 3, And just a reminder, that's not actually equal to, so we need to use the approximately equal to sign. So y is approximately equal to 1.22 times the square root of 3. All right, we have one more example here, and then we're going to get some terminology. So example 4 says to find the area of the regular hexagon below with a side length of 10. So we know that this piece is 10. And as of right now, we don't know the formula for finding the area of a hexagon. But we do know that the formula for the area of a triangle, and we'll take a second and write this down. So area of a triangle is equal to 1/2 base times height. So that's the area of a triangle. And we can turn this into triangles, and we can use this one measurement and our 30, 60, 90 formula to solve for the area of this whole shape. So the first thing that I'm going to do is I'm going to split this hexagon into some triangles, and I'm going to go from angle to angle on this one. And it's not going to be a perfectly straight line. I'm just going to do the best I can. So the center in these triangles might be a little off. As long as they are close and you know what it's supposed to be, it will be all right. So I have, there we go, 6 triangles. Now these triangles we might be able to do a little bit with, but we want to use that 30, 60, 90 triangle theorem, which is just going to make things easier for us. So I'm going to split each of these triangles in half to create 90-degree triangles, so right triangles. I'm going to pick another color. I use this green here. I'm going to split right down the side, and splitting these triangles in half, it is also splitting this 10 into 2 even pieces, so we'll have 5 and 5, which will be important, but we'll come back to that. We'll finish dividing this up first. All right, and there's the last one. It's not perfect, but it's close. When we did this, we split this into 12, 30, 60, 90 triangles. And each of those triangles looks a little something like this. So we have a 90-degree angle, we have a 30-degree angle, we have a 60-degree angle. And we know, because this was 10, that this piece has to be 5 because we cut it in half. And by our 30, 60, 90 formula, then 5 times 2 is the hypotenuse, so our hypotenuse has to be 10. And 5 times the square root of 3 has to be our second leg. So I have 5 square roots of 3. Now I can use my base and my height to find the area of this one triangle. But the thing is, we don't just have one triangle, we have 12 of them. So the area of this hexagon is equal to 12 times the area of this single triangle, which is 1/2 times the base, which we said was 5, times the height, which is 5 square roots of 3. 12 times 1/2 is 6, so what we really have is 6 times 5 times 5 times the square root of 3. 5 times 5 is 25. If we think of this in terms of quarters, 5 times 6 is $1.50, so we have 150 square roots of 3. And that is your area. And that is exact. If we wanted a decimal, we could actually type that in our calculator and find out, but that's as close as we need. So the area of a regular hexagon with side lengths of 10 is 150 square roots of 3. All right, that is the last of our solving for this section. If we turn the page, you're going to find that there's a bunch of terminology here. And before we get into it, a little bit of background here. So last section, we worked a lot with ratios and triangle similarity, which one of our theorems was the angle-angle theorem. By the angle-angle similarity theorem, any two right triangles that have another congruent angle are similar. That means that in these triangles, their side lengths are proportional, and therefore the following ratios of the side lengths are equal. And I'm not using the hypotenuse on this. I'm using my legs. So I'm going to start with this small triangle. I have FE over ED. And that ratio will be equal to ZY over YX. And that will be equal to the ratio of CB to BA. In doing that, we didn't know it at the time, but we were actually working with trigonometric ratios. You just didn't know that. And there's 3 different kinds of trigonometric ratios. The first of which is called sine, and we spell sine as S-I-N-E, but we abbreviate it to S-I-N. It's pronounced sine, and most of the time you will see the abbreviation. You won't see the full length spelling. Sine, and this sentence stem goes for all of these boxes. The what it is, it all will start with the trig function is equal to the ratio of the opposite side to the hypotenuse. So sine, in other words, is equal to opposite over hypotenuse. So if we look at an example of what exactly that means, let's start with sine of angle A. So the sine of angle A will be equal to the opposite side, which is across the triangle, that's side A, over the hypotenuse, which is C, which is our longest side and is across from the 90-degree angle. So the sine of angle A is equal to the ratio of A to C. We're going to write that out, A to C. That's how it's written, A over C. Sine of angle B is going to be the opposite side over the hypotenuse. So I have B over C. That's what we're looking at. Sine of angle A is equal to A over C. Sine of angle B is equal to B over C. Notice these pieces here are angles, and these pieces are all sides. And we actually can use our trigonometric functions to solve for both angles and side lengths, but we'll get to that in a later section. All right, our second ratio is called cosine, spelled C-O-S-I-N-E, but it is written as the abbreviation COS. And again, you'll hardly ever see the full spelling, but you will see cosine as the abbreviation a lot. So cosine is the ratio of the adjacent side to the hypotenuse. So in other words, cosine is equal to adjacent over hypotenuse. So if we were to look at an example, we have the cosine of angle A, and we have the adjacent side, which will never be the hypotenuse. So the adjacent side has to be B over the hypotenuse, which is still C. So the cosine of A is equal to B over C. The cosine of B, we want the adjacent side, which is A, over the hypotenuse, which is C. So we have A over C. All right, we have one last function here, and this ratio is called tangent, T-A-N-G-E-N-T. We abbreviate that as T-A-N. Tangent is the ratio of the opposite side to the adjacent side. In other words, tangent is equal to opposite over adjacent. And again, the adjacent side will never be the hypotenuse. So the tangent of angle A, for example, will be the opposite, which is side A, over the adjacent, again, not the hypotenuse, so it has to be B. So I have A over B. And just a reminder, adjacent means next to, so it's the side that is next to it. Tangent of B, we have adjacent, again, not the hypotenuse, so A over the opposite over the adjacent. So tangent of angle B is side B over side A. All right, so we do have a fun acronym to help us remember all of this, and that acronym is SOHCAHTOA, spelled SOHCAHTOA. And I am sure to capitalize the S, C, and T every time because those are the important pieces. That's the name of our functions. So what we really have here, SOHCAHTOA, we have the sine is equal to opposite over the hypotenuse. Then we have cosine is equal to the adjacent over the hypotenuse. Then last, we have the tangent, which is equal to opposite over the adjacent. Everything in this section is important and has a value, but I will mention that these pieces, these trig functions, SOHCAHTOA, is really important and is the basis for the rest of this unit. So I'm not asking you to do anything with these functions right now, but you do need to learn them and you will need to memorize them. And I strongly encourage you to work with this acronym to help you remember it because it is helpful, and I actually still reference this acronym when I'm thinking through them because it helps me remember really quickly. SOHCAHTOA. All right, that is where we're going to stop for today. We'll pick back up and actually do some solving with SOHCAHTOA in our next section.